Hello all. This video is aimed at providing a brief idea about estimation of figure of merit in communication systems. It is known that there exist different types of analog communication systems based on the modulation scheme used. Double sideband full carrier, single sideband suppressor carrier, double sideband suppressor carrier, vestigial sideband suppressor carrier, and frequency modulation are the different techniques that come under analog communication systems. Among these modulation techniques, which performs better is analyzed by means of figure of merit. Figure of merit can be defined as gamma equal to signal to noise ratio. Generally, we call SNR, signal to noise ratio at the output of the receiver by signal to noise ratio at the input of the receiver. This signal to noise ratio at the input of the receiver can be called as signal to noise ratio C also. Why? Because whatever coming from the channel is going to be given as the input to the receiver. That is why we can call SNR I or SNR of C. However, the signal to noise ratio in general can be defined as signal to noise ratio equal to average signal power. It is the ratio of average signal power to average noise power. Average noise power. How to get the average signal power or noise power depends on the availability of the mathematical expression. Generally, as noise is random in nature, we cannot have the mathematical expression in time domain. So, in any modulation scheme or any application, the noise power is estimated by means of an assumption. We assume the noise to be of a specific type and then estimate the noise power in the frequency domain. In the frequency domain, the power can be given as the area under the power spectral density curve. It can be represented or can be defined as the area under the power spectral density curve. For example, I want to estimate the noise of a signal. It can be given as minus infinity to infinity Sm of f df, where Sm of f is the power spectral density of the message signal, for example. However, we know the message signal or the modulated signal can be represented mathematically. Take a case, double sideband suppressor carrier amplitude modulation. What is the expression? S of t equals to AC cos omega ct into m of t. As the mathematical expression is available, in such a case, the power can be given as 1 by 2 pi 0 to 2 pi s square of t dt, where s of t is the modulated signal. As a whole, the power can be obtained in time domain if there is a standard mathematical expression available. Power can be obtained in frequency domain from the power spectral density. Once we know how to estimate the average power of a signal, then these are the different steps in estimation of the figure of merit. As we have different modulation schemes, each modulation scheme is having its own demodulation methodology. For double sideband full carrier AM, we use envelope detection. While for double sideband suppressor carrier AM as well as single sideband suppressor carrier AM, we use coherent detection. For frequency modulation, the demodulation is completely different. The frequency modulation it can be demodulated by using a limiter followed by a discriminator. That is difference. Here we convert the signal from FM to AM, that is frequency modulated signal to amplitude modulated signal. Then we use envelope detector as usual. So the first step in estimation of the figure of merit will be drawing the receiver model. This receiver model will be consisting of only those blocks that are that are affecting the signal passage, like IF section and the detector. Once this receiver model is known, we have to follow the given steps. Obtain the input signal power, obtain the input noise power. Once these two are estimated, the input signal to noise ratio is defined as ratio of the average signal power at the input of the receiver to average noise power at the input of the receiver. Once this is done, the subsequent steps are estimation of the output signal power and output noise power at the output of the detector or discriminator. Now, I will just explain you how to estimate the signal to noise ratio at the input of the receiver for double sideband full carrier AM. This can also be called as AM receivers with the envelope detection. Double sideband full carrier AM or AM receivers with envelope detection. In such a case, the AM receiver model will be consisting of, in such a case, the AM receiver model will be consisting of a mixer followed by IF section as well as the detector. Okay. However, see, this is the receiver model correspondingly. We have the adder, Y adder to the transmitted signal. The noise is going to be included in the channel, which we assume as a white noise, and then followed by IF section. What is the reason behind drawing the IF section is IF section is responsible for converting the wideband signal to a narrowband signal. This is followed by a envelope detector, right? Envelope detector. Why? Because in amplitude modulation, the amplitude is important. That is why we are going to estimate the envelope of the signal and give it as y of t. The output of the IF section always represented as x of t equals to s of t plus n of t. N of t is the narrowband noise. Why? Because wideband signal has been passed through a narrowband IF amplifier, and S of t is the modulated signal. And what is our objective? Estimation of signal to noise ratio. No? So it is known that the expression for an amplitude modulated signal is given as AC into 1 plus Ka m of t into cos omega ct. This is the expression for input signal to the receiver. Now, what is our aim? Estimation of input signal to noise ratio time being. So how to get it? It is defined as P equals to average signal power 1 by 2 pi 0 to 2 pi s square of t dt. So substitute whatever modulated signal you have. So 1 by 2 pi, estimate the individual components. 1 by 2 pi, 0 to 2 pi, AC square cos square omega ct, first component, plus 1 by 2 pi, 0 to 2 pi, AC square Ka square m square of t cos square omega ct. Square the both components present in the modulated signal. If you elaborate this, in the place of cos square omega ct, substitute, okay, AC square you can take common outside, 1 by 2 pi, 0 to 2 pi, 1 plus cos 2 omega ct. We all know cos square theta equals to 1 plus cos 2 theta by 2, right? Okay. Similarly, second expression also, AC square Ka square by 2 will be coming outside. Again, 1 by 2 pi 0 to 2 pi m square of t into 1 plus cos 2 omega ct by 2 dt, right? Upon integration, this will give you AC square by 2 into 1 plus Ka square P. That's it. This is the input signal power. You can call either a P or SI also, no problem. I'm just mentioning as P, SI also. Once it is done, the next step is to estimate the input noise power. This step is very vital. Input noise power estimation is common for all modulation schemes. The noise power, as no mathematical expression for noise is available, it can be represented or obtained from the frequency domain as minus infinity to infinity SW of F df. Why? Because power spectral density, we assume what is the power spectral density at the input side, that is considered as white noise. White noise representation is SW of F equals to N naught by 2. Okay, so this input noise power is always estimated for message bandwidth only. So that is how it can be given as N naught by 2 df. This is equals to N naught by 2 minus W to W into 1 df. Integration of 1 with respect to f is f. df is 1 only. So it gives you finally N naught into W. So this is the input noise power. So finally what you can have is a signal to noise ratio at the input of the AM receiver is AC square into 1 plus Ka square P by 2 Wn naught. 2 Wn naught. The same manner, you can obtain the figure of signal to noise ratio at the input for other modulation schemes also.